Well, hello everybody, and let's just keep trucking along on chapter 12 here. This lecture, different from most weeks where we split a chapter over 2 different days, this lecture rehashes a lot of what we talked about in the previous video, but goes into much more detail of the actual proteins that do the work, how those proteins work, ion channels specifically. And then we have a nice little mini unit on the nervous system, because that's where ion transport is most important. So this will be pages 419 to 442 in the textbook. And today we're going to go back to the membrane potential and talk about that again, but again, give a little more meat on the bones of that. That'll bring us back to ion channels, but we'll also speak about those in much more detail than we did in the last video. Talk about how ion channels are regulated and how membrane potentials are also leveraged by the cell and regulated. That'll lead us into a discussion on voltage-gated ion channels specifically, although we will talk about other gates. And as I'm already mentioned, we'll end with a little mini unit on neurons in the nervous system. So circling back to a lot of the concepts we introduced in the last video, if something has charge, whether it's partial charge or full charge, that thing is not going to passively diffuse across the membrane, especially if it's ionic, especially if that charge is full. The one caveat to that is that passage across the membrane is possible as long as the diffusion isn't passive. In other words, if it's facilitated diffusion. If we have a hydrophilic channel, a transmembrane protein that allows that charged particle through, that's the doorway through the wall of the cellular membrane. And though there are rare examples of wide, completely promiscuous, nonspecific channels that allow nearly anything through it, that's definitely the exception. The vast majority of channels are narrow and specific for one specific ion or at least a limited number of very similar ions. And again, by ions, we mean solutes, right? The cell's life itself is nothing more than a bag of water. And so these are ions that are dissolved in water. These are solutes. What makes a channel specific and not just this wide open doorway that anything can get through is due to what we refer to as a selectivity filter. So you can kind of see a selectivity filter here in this figure from the textbook, but essentially it's a narrowing of the channel, and the diameter of the channel at this narrow part is specifically the size of the ion that we hope to select for. So it's really all based on size and then charge, of course. Whether it's a cation or an anion, there's going to be charge to that. And so the side chains of the amino acids that line the selectivity filter will have the opposite charge, and that helps coax that ion through. So if it's a cation channel, then we're going to see negatively charged side chains in the selectivity filter, and vice versa for anions. The side chains will be positively charged so that we're not repelling the very ion that we want to allow through. And so again, selectivity is based on size, the diameter of the ion, and that's going to be the diameter of the selectivity filter, and of course the charge as well. What I find nearly science fiction, more amazing than just a selectivity filter, is that most ion channels are gated, and I've already kind of hinted at that in the opening slide. By gated, we mean that these channels can have an open state and a closed state where the gate is closed. And so the channel itself can be regulated, allowing ions through when the channel is open and blocking even those specific ions when the channel is closed. So these are due to conformational changes in the channel protein. The protein changes its shape, and change of shape, of course, changes function. And so one particular conformation would be the open conformation, and ions can get through, and another conformation would be the closed, and ions can't get through. And these channel proteins are fluctuating between open and closed based on some kind of cellular signal, cellular stimulus or input, some message that it's getting that ions are needed or not needed. Despite all this complexity, and it's already getting complex, I'm aware of that, don't forget that channels are channels. They're not pumps and they're not transporters. They're only engaging in facilitated diffusion. They are open doors when the gate is open that ions can then diffuse through following their gradients. They provide a way for polar charged things to move down their concentration gradient or down their electrochemical gradient, which we'll talk about in just a second. But there's no action here. There's no energy. There's no moving parts other than the gate. There's no active transport. There's no energy requirement. Channels are not pumps. Channels are not transporters. Channels are channels. And even if they're open and closed, even if there's a selectivity filter, it's just a portal that things can diffuse through. So once a channel is open, if it's gated, All channels are doing is letting things flow and follow their natural gradient. And if that gradient is severe and there's a lot of potential energy and wanted flow, then you better believe those ions are going to flow rapidly and generate a lot of kinetic energy. In fact, ion movement through an open channel is about 1,000 times faster than the fastest transporter. And that's, of course, because transporters have moving parts, and those moving parts slow the diffusion down. Channels are just an open doorway, so things can flow through that open doorway as quickly as they possibly can. Again, no energy required. It's not active transport. No movement. It's not a transporter. Just ion diffusion, just ions floating through an open door. Most of the time, this very valuable kinetic energy of this very rapid ion flow is leveraged by the cell. The cell is going to use that for a lot of different processes, some of which we'll talk about at the end of this video. And so cells are constantly regulating and monitoring and manipulating the electrochemical gradient of specific ions. And hopefully you remember from the last video that an electrochemical gradient is a gradient that considers both the concentration gradient of the ion and its charge. Right? If we have more cation on one side of the membrane than the other, we would expect that cation to want to flow down its concentration gradient. However, if on the low concentration side of that membrane, we've got a whole lot of other positive charge, well, now we're putting an opposing repulsive force. So the electrical chemical gradient takes into the account the concentration gradient and the charge of the ion. In the example here, it's the opposite of what I just described. This is a very strong electrochemical gradient. As I look at this, I see that positive sodium outside the cell has a much higher concentration outside the cell than inside. So if we just consider the concentration gradient, sodium wants to flow from out to in. And if we look at the charge, it's a lot more positive outside the cell and it's a lot more negative inside the cell. So from a charge perspective, sodium wants to flow from out to in. So in this scenario, the electro and the chemical gradient are both pushing in the same direction, outside to in, creating a great deal of potential energy. Sodium desperately wants to flow across this membrane. It can't passively diffuse because sodium is charged and we have the lipid bilayer. But if we give sodium a channel, again, boy, oh boy, will it flow. And that potential energy will become kinetic. So this pent up wanted energy of flow that sodium is exhibiting here, this potential energy is referred to as a membrane potential because it's potential energy across a cellular membrane. And when the channel opens, that potential energy becomes kinetic, becomes energy of motion because the ions are in motion. So when we do this, when we deal with charged particles that are being considered, we're talking about electricity. And most of the time when we talk about electricity, we're talking about electrons, and that's why it's called electricity. But truly, the principles, the fundamental principles of electricity depend on the movement of ions, whether they're electrons or any other kind of ion. And when ions move, we call that current. Again, if you plug something into the wall and electrons are moving, we call that current, but current is the movement of ions. And so when sodium moves, that's a current. It's current of sodium. And we can measure current in units of amperes, amps. And amps is measuring kinetic energy. It's measuring flow, the flow of ions, the movement of ions. And so amps are measuring kinetic energy. When charged things can't move, however, we have a potential, right? They're charged, they want to move, just like water wants to move when it's dammed. So we call this a potential energy. And electrically, we apply the principles of electricity to potential energy. That's what's measured in volts. And so whether you have a fan, a light bulb, or nothing plugged into the wall, that outlet has 120 volts. I think it's 120. Maybe it's 110. I don't know. Whatever the voltage is in the United States, that's the voltage of an outlet, whether something's plugged into the outlet or not. That's the potential energy of wanted electron flow. If you do plug a light or a fan into that outlet and you run that light or fan, now you're also generating amps. You're generating current because the electrons are in motion. And so we want to keep these principles in our mind because we're about to talk about sodium and potassium and calcium flowing. And when sodium wants to flow, but it can't, we have a voltage, we have a membrane potential. And when sodium wants to flow and a channel is open and it actually is flowing, well, now we're generating amps. We're generating a current, an electrical current. if we consider the cellular membrane, the inside of the cell is largely negative. We've talked about that in the last lecture. We have those anions, those intracellular anions that are in there. And the outside of the cell is largely positively charged. Sodium's out there. Of course, opposites attract. The positive sodium outside the cell wants to get to the negative charges inside the cell. So that's driving some of the potential energy. Sodium wants to flow because it wants to get to negative things. And it can't because the membrane is impermeable to sodium. So we've got a potential there. We've got potential energy. Ion channels aren't always open. And that potential energy is the potential energy of wanted sodium movement across the membrane. And every cell has a membrane potential. Some cells have a much starker membrane potential. They have more volts across the membrane because they have a much starker or more severe electrochemical gradient of those ions. And some cells have a more weak membrane potential with a lower voltage because the not so much of a stark gradient, but every cell has a membrane potential. And we see that example here. On the right, we have a balance of positive and negative charges. We have an ion channel, but it doesn't look to me like anything's going across it because everything's at equilibrium. There's no wanted flow here. All the positive charges are equally distributed. All the negative charges are equally distributed. There's no concentration gradient. There's no electrical gradient. There's no electrochemical gradient. We've got a membrane potential of 0. There's no potential energy here. But if we look at the diagram on the right, well, now we've got more positive charges on one side than the other. We've got more negative charges on one side than the other. So the positive things want to move from high concentration to low concentration. Simultaneously, they want to move from more positive to more negative. And the negative charges want to flow in the opposite direction. There's energy of want here. There's potential energy of things that want to go through the membrane. Doesn't look like they're going through the membrane to me right now. It appears like these channels are closed. And so we have a membrane potential. But if those channels open and those ions start to flow, we'll generate a current in amps. We'll have kinetic energy. The membrane potential when the cell membrane is at rest for most cells is somewhere between -20 to -200 millivolts. Again, a wide range depending on cell type, but that's the resting membrane potential. Most cells are maintaining a membrane potential of -20 to -200 millivolts. And again, we're measuring it in volts because it's potential energy. It's potential energy of wanted flow. And the reason why it's negative is, of course, because most of the things inside the cell are negative, right? We've got all those anions inside the cell. We've got chlorine inside the cell. And so the inside of the cell is more negative than outside. So the membrane potential itself is negative. Cells use these membrane potentials for lots of things, but most notably, the entire functioning of our nervous system depends on electricity. It depends on ion channels opening and closing, ions moving. It depends on volts becoming current. And by altering the membrane permeability to different ions, by opening and closing different channels for different ions, neurons finely tune and control these membrane potentials and use those membrane potentials to conduct information, to send signals. Just a reminder of kin, our nice mnemonic. Potassium, or K, is much more concentrated inside the cell. That's how we start. We start with potassium, even though it's a cation. We start with potassium inside the cell, and we start with sodium outside the cell. And most cells, including neurons, have what are referred to as potassium leak channels. They're called leak channels because they are meant to allow potassium to leak through them. Potassium leak channels are ungated, or at least they're always open. And because they're always open, they, in theory, potentially, allow potassium to move in whatever direction it wants to. But when a cell membrane is at rest, potassium doesn't move. Despite there being much more potassium inside the cell than outside the cell, there's a whole lot of sodium. And sodium is positively charged and potassium is positively charged. So all that sodium outside the cell repels potassium. Not to mention that there's a lot of negative charges inside the cell. That's why the membrane potential is negative. There's those anions, there's chlorine, so potassium being positively charged likes being around those negative things. And so the electrochemical gradient of potassium is balanced. And there's no potential energy, there's no wanted energy of ion flow for potassium. The chemical gradient is pushing potassium out. The electrical gradient is keeping potassium in, and those two gradients cancel each other out, and the net force on potassium is nothing. if something were to change, and we'll see things change in a little while, if the inside of the cell becomes more positive, maybe perhaps because sodium rushed in, well, then that counteracting, that opposing force on potassium's chemical gradient is no longer there. And potassium will begin to, and I'm making air quotes, potassium will begin to leak across the membrane by going through these open leak channels. But when the membrane potential is at rest before anything happens, for potassium, largely these two forces, the electrical force and the chemical gradient force, are balanced and potassium is at an equilibrium. For every potassium ion that does leak from inside to out, another potassium ion is leaking from outside to in, and the net movement of potassium ions is zero. Not so for sodium, right? As we've said before, sodium has its chemical gradient pushing it inside the cell. It has its electrical gradient pushing it inside the cell. Sodium wants to flow from outside to in because of its concentration gradient and because the inside of the cell is so negative. So for sodium, we have a membrane potential. We have a potential energy of sodium wanting to flow. And if a sodium channel were to open, as we see here, sodium is going to flow. And the flow of ions across a membrane, including sodium, because sodium is charged, is a current. It's generating amps, and we can measure those amps. It's also changing the membrane potential, because the membrane potential is a measure of energy of want. And as sodium flows, its energy of want goes down and down and down, right? As water flows across the dam, and both sides of the dam have more and more equal levels of water, then the driving force moving water across that dam begins to lessen. The way we can measure this experimentally is that as sodium rushes inside the cell, the membrane potential becomes less and less negative. Or another way of saying that, as it says on the slide, is making it more positive. Sodium is bringing that positive charge, its positive charge, into the cell, and the membrane potential gets more and more positive. Now remember, ion channels are highly selective because of that selectivity filter, and they only let their specific ion through. So only sodium can go through sodium channels, and only potassium can go through potassium channels. And that allows the cell to finely tune and control everything that's occurring across the membrane. As sodium comes rushing in, and the membrane potential becomes more and more positive, this change in membrane potential can be reversed, and we can restore the membrane potential back to its original state. But to do that, we need other ion channels to open as well. What does this imply? It implies that ion channels are opened and closed in a very precise and highly controllable and regulatable way to manipulate, control, and restore the membrane potential. And that's true. We already know that's true. That's why ion channels are gated. The reason why ion channels are gated is so that cells can control when they're open and closed, control the movement of ions, and thereby control the membrane potential itself. And lots of things can control the gate of an ion channel. In other words, lots of different stimuli can control what opens and closes a channel. And so let's talk about the different kinds of channels that exist and the different kinds of signals or stimuli that can alter that state of the channel. First, and most importantly, are voltage-gated channels. Voltage-gated channels will play a major role in the rest of this video. Here, the channel is opening due to a change in the voltage of the membrane. But let's not get lost in that term voltage, right? What is volts measuring? It's measuring membrane potential. And what is membrane potential measuring? It's measuring energy of want. So all we're saying by a voltage-gated channel is as the want of ion movement changes, these voltage-gated channels can open or close, right? That's all that we're measuring in voltage, is the potential energy of ion flow, ions wanting to flow. For voltage-gated channels, there's a part of the protein that's very sensitive to changes in the membrane potential, very sensitive to ions wanting to flow. And as the membrane potential changes, as it gets more negative or more positive, as ions are flowing, the voltage sensor is going to move. There's going to be a conformational change. And that conformational change will either result in the channel opening or closing, depending on the channel. So for voltage-gated channels, we see these all the way on the right here. We see on one specific membrane potential at one measurement of millivoltage across the membrane, which is a measure of wanted ion flow. the channel is closed. But as the membrane depolarizes, in other words, as some ions come in through another channel, as some ions come in through some other process, and the membrane potential in this example gets more positive, look what happened, right? Inside is positive. Now, as we are no longer as negative as we were before, we have a change of potential across the membrane. We have a change in voltage across the membrane. We're going to see this membrane channel open, this voltage gated channel open. So as the membrane potential changes, because ions have flowed in other ways, the voltage sensor is going to move through a conformational change, and the state of the channel will change. So in a very real, specific way, the channel state, open or closed, is controlled by potential energy. It's controlled by voltage across the membrane. There are ligand-gated channels, which aren't as complicated. In a ligand-gated channel, a ligand, and remember that's just a term for something that can bind to a protein. So antibodies have ligands, we call those antigens. Enzymes have ligands, we call those substrates. Some channels have ligands, something can bind to the ligand. And sometimes that thing binds to the ligand from the outside, so it's an extracellular ligand. Sometimes that thing binds to the membrane protein from the inside, that's an intracellular ligand binding. Sometimes when the ligand binds, the channel opens. Sometimes when the ligand binds, the channel closes. But the net result is that the state of the membrane channel is controlled by the binding of a ligand. So some other molecule binds to the channel, and in this scenario, opens it, or something binds to a channel and closes it. What kinds of things do we mean? What are the ligands? Well, some common examples are cyclic AMP, which we'll talk about in our cellular signaling lecture in like 3 weeks, I think. Hormones, of course, are going to control this as well. There's an enormous amount of integration and interplay between the endocrine system and the nervous system. So we see hormones doing this a lot, or many, many other examples. There are mechanically gated channels. These are really interesting because what causes a mechanically gated channel to open or close is pressure, is mechanical pressure. So some pain receptors are mechanically gated. When you press hard enough on your skin, you press hard enough on a nerve ending, and it can hurt. And that's a mechanically gated channel. We're going to see a truly stunning example of a mechanically gated channel in just a second as well. But generally speaking, physical stress, mechanical stress, pushing, squeezing, etc., causes the channel to open. And when the channel opens, ions flow. So again, touch, pressure sensors in your skin, pain sensors in your skin, a lot of our stimuli, a lot of our sensation is through mechanically gated channels. So here's the example. You ready for this? Mechanically gated channels is the fundamental mechanism of hearing, of the sense of hearing. So how this works is that we have auditory hair cells in our ear. So this is a portion of the eardrum. So this is what vibrates as sound waves hit our ear. Sound waves are nothing but pressure waves in the air, right? You need air or some medium, air, water, some medium to carry those waves. So you have a sound. That sound is really just the changing of air pressure. And so as that sound comes into our ear, that change in air pressure makes our eardrum vibrate. And the tectorial membrane of the eardrum is vibrating. Okay, so that's the input of the pressure waves of sound to our ear. As that tectorial membrane vibrates, as those air vibrations hit our eardrum, the eardrum pushes on these hairs, these auditory hairs that are in our inner ear. As those hairs are stressed and moved, right, as the eardrum vibrates and stresses or pushes on these hairs, that movement of pushing, that pressure of pushing, causes mechanically gated channels to open. Once mechanically gated channels open, ions flow because there was a membrane potential, voltage becomes amps, potential energy becomes current. That neuron fires as a result of those ions coming in, and that firing of the neuron sends that signal, that message, that auditory information to the brain, and then the brain processes it and tells us what we've just heard. So as you're listening to my voice now, what's actually happening is that my voice coming through a speaker or an earbud is causing pressure changes in the air. Those pressure changes in the air are causing your eardrum to vibrate. As your eardrum vibrates, those vibrations are pushing on and straining these auditory hairs. As those hairs are pushed on and strained, they're causing mechanically gated channels to open. As those mechanically gated channels open, neurons are firing because ions come pouring into them. And those firing neurons are transmitting that information of vibration to your brain so that you can experience the sensation of hearing. So we hear by touch, we hear by pressure. And just as your fingers can feel pressure as you touch and hold things, your ear can feel pressure in the same exact way. And we experience that pressure as sound. So all ion channels are constantly in this flux between opening and closing. And that depends, of course, on how it is gated and the stimuli that are causing those channels to open or close. Even a closed channel opens occasionally. Remember, there's dissociation constants and all kinds of constants for every single kind of protein. No protein stays in one state permanently. So when we say a channel is closed, we really just mean it's closed most of the time and it opens infrequently. And when we say a channel is open, we mean that it's open most of the time and closes infrequently. But they're constantly fluctuating between these two states. The implications of that is that membrane potentials aren't quite absolutely steady. They're always fluctuating, positive and negative around a baseline. So even if a membrane potential is minus 20 millivolts, you measure it at one point, it's going to be minus 19, minus 18. You measure it again, it's going to be minus 21, minus 22, all depending on these channels sporadically opening and closing, kind of as the static noise of a biological system. But when our ion channel is opened by some stimulus, mechanical stimulus, voltage-gated stimulus, ligand stimulus, it's now more open than not. Ions flow more than not, and the changes in the membrane potential are more dramatic. So all that changes here, depending on the signal of the channel, is again the proportion of time where the channel is in one state versus the other. When channels are open, regardless of what kind of channel it is or what opened it, ions are going to flow, and as ions flow, potential energy becomes kinetic, membrane potentials change. And this change in membrane potential serves as an electrical signal, an electrical trigger for lots of different cellular processes. It can set off a cascade of other channels opening. It can set off pumps kicking on to restore the membrane potential. It can, again, transduce the information of audition to the brain so that the brain can experience hearing. All that can happen until eventually, whatever caused those channels to change their state reverses. The cell goes back to its resting position, its resting state, and the membrane potential will be restored. All right, so I think we've got enough now under our belt where we can talk a little bit about the nervous system and give some real case studies, some specific examples of how these wonderful systems come together to allow the human condition to be, allow us to be self-aware, allow us to experience the world, use our senses, allow us to actually contemplate how it is that we contemplate. We are now going to use the brain to try to understand how the brain understands things. Pretty meta. So the central nervous system depends on and revolves around membrane potentials, the movement of ions. And that means that it depends on voltage-gated channels. These channels have domains that are, again, extremely sensitive to changes in the membrane potential. And when a certain threshold potential is reached, the channel is going to open and spend a lot more of its time in the open state than in the closed state. That's going to allow ions to flow. Potential energy will become kinetic energy. Ions are going to flow following their electrical chemical gradient, and the membrane potential will change. It will change dramatically, and it will change quickly. Because of the ions that are flowing into the cell now, this is going to trigger additional ion channels to open, and that's going to propagate the signal down the membrane. Also, or either, other cellular processes can also occur, like transmitting that signal to the next cell so that the message can continue. So what we're really dancing around here is the anatomy and physiology of a neuron. And a neuron is, of course, the fundamental cell of the nervous system. And the neurons have two distinct parts that allow them to do their job. The axon, which is the specialized portion of a neuron that allows it to send a message. And the sending of that message, the electrical signal that is being sent down the axon, is called an action potential. So what is an action potential? An action potential is the actual message. It's the signal that is being sent by one neuron to some other cell. And if it's the axon that allows the action potential to be transmitted, we can think of the axon as the neuron's mouth, the thing that articulates the signal, the thing that carries the signal, that transmits the signal. The other part of a neuron are the dendrites. If the axon is a neuron's mouth, then the dendrite is the neuron's ears. The dendrite is how a neuron receives information from a previous cell. So if we consider this one neuron in isolation that we see on the screen, some other neuron shouts a message down its axon and transmits that message to this neuron. This neuron receives that message through its dendrites. That's the ear or the antenna of this neuron. And now that neuron is going to relay that signal down its axon and shout it through that axon mouth to the next cell. And the next cell will receive that message from its dendrites and so on and so on. When a neuron does receive a signal to fire from a previous cell, that firing is the action potential. That firing of a neuron is a change in the membrane potential, initially locally, and then systemically across the entire cell, where membrane potential changes. Well, what does that mean, membrane potential changes? It means ions are flowing. Well, why are ions flowing? Because they have an electrical chemical gradient, and that means voltage is becoming amps. Ligand-gated channels open, ions rush in, the membrane potential changes locally. That's going to trigger additional voltage-gated sodium channels to open. Now sodium's going to come rushing in and we change the membrane potential more systemically. And there it is. Boo! We get an action potential. Get an action potential. Let's take a look at what's happening here. We're starting at our resting membrane potential. For this particular cell, the resting membrane potential is negative 40 millivolts. Okay, membrane's at rest. What happens? Well, the cell receives a signal from a previous neuron. And that receiving of a signal, we'll talk about that at the end of the video today, but that receiving of the signal for now opens ligand-gated channels, ligand-gated ion channels. Because those ligand-gated ion channels open, ions start rushing in, and the membrane potential climbs, just slightly climbs. But the membrane potential is changing. It's getting more positive. And when we reach a certain threshold, that threshold is sufficient to now pop open those sodium channels. Sodium channels open, and now sodium comes rushing in, carrying in all that positive charge with it. And this is the peak of the action potential. That message has gone fired down the axon and is allowing that neuron to speak to the next one. But the cell needs to reset, needs to be ready for the next action potential. And so to do that, we're going to pump that sodium out, allow potassium to come back in, and we're going to restore the membrane potential back to rest. And we're going to go back to a resting membrane potential. It's negative. So once again, sodium wants to rush in because everything has been reset and the axon and the overall neuron is ready to do it again. So this is depolarization. When we go from negative to positive, when we go from sodium outside to sodium inside, we have depolarized the neuron. When sodium comes rushing in to the axon, of course, that sodium is going to diffuse down the axon. It's going to go from where it's most concentrated to where it's least. So sodium comes pouring in through specific channels, and once in the axon, that sodium is going to distribute up and down the axon. It's going to change the membrane potential. Well, since the membrane potential is changing in that area, the next set of sodium channels down the axon are going to pop open. Sodium's going to come rushing in there. And that sodium that came rushing in is going to diffuse, and that's going to open the next ones. What's really happening here is this. You can think of the fans that are standing as the opening of sodium channels and sodium coming rushing in. But what happens when one segment of the crowd stands? Well, that triggers the neighboring segment to stand, which triggers the neighboring segment to stand, which triggers the neighboring segment to stand. And what happens to the fans that started it? Well, they sit back down and reset. So action potentials are the wave, but it's a wave of sodium influx. So here we see it. Sodium channels are open. Sodium comes rushing into the axon. But as soon as sodium is in that axon, that sodium diffuses left and right, left and right. For reasons we won't get into too much here, the sodium channels that had opened just a minute ago, these are the fans that just sat down, they're in a refractory period. They're not going to open again right away. So the action potential can't go to the left. But these sodium channels are naive. They haven't stood up for the wave yet. So as this sodium that just rushed in diffuses to the right, that's going to get these sodium channels to their membrane potential, to their threshold potential, excuse me. And because they reach their threshold, they're going to pop open. And they pop open and sodium comes rushing into those. Well, what's that sodium going to do? It's going to diffuse right and left. Well, the sodium that diffuses left isn't going to do anything because these fans just sat down. These channels just closed. They're refractory. But these channels haven't been open in a while. So these sodium channels open. Sodium comes rushing in here, which is going to make these channels open. Sodium comes rushing in here, which is going to make these channels open. And you get the wave. You get the propagation of sodium flow from left to right down the axon. That's an action potential. That's all it is. That's the brain firing. That's the transmission of information. Voltage-gated sodium channels have three states. They've got the closed state, they've got the open state, and then they have this refractory state. So closed is when the membrane potential is at rest. That's a channel that hasn't been doing anything in a while. Fine. Open, of course, is when we reach the membrane potential threshold. The channel pops open, sodium comes rushing in. But when that channel closes again, after having been just opened, it's inactivated. There's a domain, there's a portion of the channel that plugs itself shut so that it can't open again soon. It's refractory. And this inactivated form allows that patch of the axon membrane to repolarize and not fall into this trap of letting the action potential move in both directions. These channels are open, these channels are closed, and these channels are inactivated. These channels are open, these channels are closed, and the fans that just sit down are refractory. They're inactivated, and that keeps the wave moving in one direction. It also helps the membrane potential reset. It gives the neuron and the axon a moment of rest where the membrane potential can be reset. Sodium and potassium can go where they are, where they belong, and we don't keep firing a signal that might not be physiologically relevant anymore. Helping the membrane potential reset are voltage-gated potassium channels. As sodium comes rushing in and we get this massive depolarization of the cellular membrane, inside the cell becomes much more positive. Potassium channels are going to open because of that extreme change in voltage. And now potassium is going to begin to leave because remember, what was keeping potassium in the cell was that the inside of the cell was much more negative. With all the sodium rushing in, now the inside of the cell is much more positive. And so potassium begins leaving as a result of that. That's what we see here. So here we have the membrane at rest. Right here, we reach the threshold. So sodium channels open. And this is mapped to here, sodium channels closed. We're at rest. We reach the threshold, open. Once those sodium channels open, woo, look at all that sodium come rushing in. As your depolarization inside of the cell gets a lot more positive. Well, that's going to cause the sodium channels to go refractory. Sodium channels will inactivate, but this huge change in membrane potential is going to pop those potassium channels open. Potassium channels are open and potassium goes rushing out. That's what restores the membrane potential initially, is the outflux of potassium. We're back to the membrane potential, and now the sodium channels are out of their refractory period, and the potassium channels are closed as well. Only the leak channels remain open. So we have this nice threshold, sodium comes rushing in, so much sodium is in that potassium goes rushing out. Potassium rushing out reestablishes the membrane potential, but then we want to reset everyone and create the gradient of sodium again. And for that, we need our old friend, the sodium-potassium pump. Remember, this pump is responsible for 30% of your consumption of ATP. And here is one of the ways that this pump is critical for human survival, because it is the sodium-potassium pump that resets neurons to their starting space. Just because we got back to our resting membrane potential here doesn't mean the neuron is fully reset. In this state right here, there's a whole lot of potassium outside the cell, and there's a whole lot of sodium inside the cell. And this neuron can't fire again in those conditions. So in order to make the neuron fireable again, we need the sodium potassium pump to reverse that trend and get sodium out and potassium in so that the neuron's been restored to its initial starting position. All right, so that's great for one neuron. But how do messages get transmitted from neuron to neuron? What made the neuron that just fired fire in the first place? And how does this neuron that just fired get the next one to fire? How do we play the game of telephone from neuron to neuron throughout the nervous system? So, as that action potential goes down the axon in the way that we described, it's going to eventually reach the end of the axon, where sodium comes rushing in at the axon terminal. But when you're at the axon terminal, there's no more place for sodium to diffuse. There's no more axon to continue to transmit that information. So what happens then? Well, at that point, the signal now needs to be passed from the current neuron to the next one so that the process can continue there. And neurons connect to one another and transmit information between each other at structures called synapses. Now, at a synapse, interestingly, neurons don't ever physically touch each other. There is intracellular space between neurons. It's about 20 nanometers. And so there's 20 nanometers of a gap from neuron to neuron. To span that gap and have the information jump that gap and continue to the next neuron, we have to transform or change the electrical signal that was just in the axon to a chemical signal that can diffuse across the synapse. And the chemical form of a neuronal signal is a neurotransmitter. Neurotransmitters are molecules, they're chemicals that are released by a presynaptic neuron when that action potential wave hits the end of the axon. Neurotransmitters are released. Neurotransmitters diffuse across the synapse, they diffuse across that 20 nanometer gap. Neurotransmitters bind to the postsynaptic cell, the next neuron, and those neurotransmitters are ligands. And they bind to, say it with me now, ligand-gated channels. And when those neurotransmitters bind to the ligand-gated channels, those ligand-gated channels open. Ions go rushing into the dendrite. That changes the membrane potential at the dendrite. That change in membrane potential is going to cause voltage-gated channels to open. Sodium is going to come rushing in. Sodium comes rushing in, diffuse it to the right, diffuse to the right. Next sodium, got a wave, crowd of the wave, go to the axon terminal, right? Like, so the whole thing repeats in the postsynaptic cell. So if we see that graphically, here is the presynaptic cell. So that fan wave, that action potential, that flow of sodium has just arrived here at the axon terminal. And as a result of the membrane potential changing here at the terminal, neurotransmitters will be released. The neurotransmitters diffuse across the synaptic cleft. They bind to these ligand-gated, these neurotransmitter-gated channels in the postsynaptic cell. Those channels open, ions go rushing into the postsynaptic cell, you have a change in membrane potential, and we're back to an electrical signal. We've gone from electrical to chemical, back to electrical in the postsynaptic neuron. Give a little bit more detail to this. When the action potential reaches the axon terminal of the presynaptic neuron, what actually opens there in the axon terminal are voltage-gated calcium channels. Calcium is positively charged, so it comes rushing in following its electrical chemical gradient. And that's the signal for neurotransmitter release. When calcium comes rushing into an axon terminal, it causes vesicles, membrane bubbles that are preloaded with neurotransmitter. Those vesicles fuse to the axon terminal membrane and they dump their contents into the synapse. We call them synaptic vesicles because they solely exist for releasing things into the synapse, but they're vesicles. They're preloaded vesicles containing neurotransmitters waiting to be released, waiting to be fused to the membrane. And the signal that causes that fusion is the influx of calcium. So sodium, 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 wave, right? A fan wave at the arena. The sodium flow reaches here, the axon terminal. That changes the membrane potential in the axon terminal because sodium is an ion, it's positively charged. That change in membrane potential, that change in voltage, causes voltage-gated calcium channels to open at the axon terminal. Calcium comes rushing in, and as a result of that increase in intracellular calcium, the vesicle fuses with the presynaptic membrane, and its contents, the contents of the vesicle, are dumped into the synaptic cleft. And those contents are neurotransmitters. Neurotransmitters bind to the ligand-gated channels on the postsynaptic cell. Those channels open, ions come rushing in, and we're right back to a chemical signal. I'm sorry, an electrical signal. We're right back to the flow of sodium, causing an action potential to trigger in that next postsynaptic neuron. And that's what is here in words. Once we have triggered the postsynaptic neuron to fire, and we've successfully transmitted our neurotransmitter signal, the neurotransmitters in the synapse need to be removed so that that system can reset. There's two main strategies to remove neurotransmitters from the synapse. Sometimes, for specific neurotransmitters, they're gathered and pumped back into the presynaptic cell. They're recycled. They're loaded into new vesicles and ready to do it again. And sometimes, for different kinds of neurons and different kinds of neurotransmitters, there are enzymes already floating in the synaptic cleft, and those enzymes are there to destroy the neurotransmitter. So once the neurotransmitter is in the synaptic cleft, they're immediately degraded and destroyed by those enzymes, and that stops the signal from being transmitted for longer than necessary. Interestingly, neurotransmitters fall into two main classes, excitatory and inhibitory. Excitatory neurotransmitters make it easier for the postsynaptic cell to fire an action potential, so they are stimulating. And inhibitory neurotransmitters make it harder for the postsynaptic cell to fire. They are depressing the activity, depressing the action potential of the postsynaptic cell. How this happens physiologically is that when the neurotransmitter binds to a channel and allows positive ions in, well, that's going to be excitatory because that's getting us closer to the threshold. When a neurotransmitter binds to an anion channel and allows negatively charged ions in, we're further polarizing the membrane. We're making the membrane potential more negative, getting us further and further away from the threshold, making it harder for that postsynaptic cell to fire. So what makes a neurotransmitter and a signal excitatory or inhibitory really boils down to the type of ion that it's allowing in. You're allowing in a positive ion, you're moving closer to the threshold, you're making it easier for an action potential to fire, you're exciting the neuron. If you're allowing an anion in, you're making the membrane potential more negative, you're getting further away from the threshold, you're making it more difficult for that action potential to fire. And then we can just wrap up with what some drugs do and how we actually think, or how we think we actually think. So, drugs that treat insomnia, anxiety, depression, schizophrenia, as well as sedatives and tranquilizers like barbiturates, Valium, Ambien, which is used for sleeping, all of these drugs all work through the GABA system. They bind to receptors that the GABA neurotransmitter typically binds to, but the drug opens those receptors. What is GABA? Again, it's an inhibitory neurotransmitter. When GABA binds to a channel, anions are allowed in. What do anions have? Negative charge. When they're allowed in, what happens to the membrane potential? It gets more negative. If the membrane potential is getting more negative, you're moving further away from the threshold. You're making it harder for that neuron to fire. You're suppressing neuronal signaling. You're suppressing stimuli. Well, if you have insomnia and you're depressing the nervous system, you're getting sleepy. If you have anxiety or depression and you're dwelling and focusing on stimuli and affecting your mental health, you're depressing the nervous system. By depressing, I don't mean making sad. I mean inhibiting, tamping down, silencing. Tranquilizers, Valium, right? You're all keyed up because you're about to have surgery. Take a Valium, open those GABA channels, let anions into your neurons, make it harder for those neurons to fire. Ooh, I'm not really all that upset at all. My heart is beating slow, feeling pretty chill. Go ahead and cut me open, doctor, because I'm not really all that anxious at all. That's my nervous system being suppressed. Antidepressants like Prozac. Most of those are SSRIs. You might have heard that term before. Well, what does SSRI stands for? Selective serotonin reuptake inhibitor. Ooh, reuptake. Well, that sounds like a pump, something that's absorbing serotonin. What's serotonin? Serotonin is a neurotransmitter. So serotonin is one of those recycled neurotransmitters. There aren't enzymes in the synapse that break serotonin down. Instead, when serotonin is released, pumps are in the presynaptic cell that gather that serotonin and pump them back into vesicles so serotonin can be recycled. The more active those pumps are, the quicker serotonin is gathered from the synapse. SSRIs, selective serotonin reuptake inhibitors, turn those pumps down, keep serotonin in the synapse for longer. As serotonin persists in the synapse for longer, that serotonin continues to send its neurotransmitter signal to the postsynaptic cell. That allows serotonin to exert its effects for longer. And for reasons that I'm certainly not entirely clear on, and from what I've read in the literature, it's pretty clear that medicine and science doesn't even fully understand. If you keep serotonin around in the synapse for longer, some symptoms of depressive mood disorder are alleviated. We're not quite sure why, and we're not quite sure how. There's a huge number of neurotransmitter receptors. I want to be clear, we're just touching on a very, very small few of them here. But all of those neurotransmitter receptors and the neurotransmitters that bind to them fall into a very limited number of classes based on the neurotransmitter, based on its ability to excite or inhibit, and based on the effects that it has on the nervous system specifically, and the individual or the organism more generally. So all that might lead us to what we really wish we understood and had an answer to. How do we think? How do we learn? What is the biological mechanism of consciousness? If we understand the nervous system as thoroughly as we seem to here, certainly we can understand how we think, remember, learn, understand, and exist. Not so much. Neuroscience is still in its infancy field, and it's an infant field with an extremely complex system that it needs to study. In fact, my doctoral advisor used to half joke but half seriously say all of today's neuroscientists are just keeping the bed warm for technology and computational power to catch up to what we really need in order to understand neuroscience to its fullest potential. And that's probably still true. No offense to my wife, who's a neuroscientist, but I don't think any neuroscientist who's practicing now could have any reasonable hope of ever living long enough to see these questions answered. They're just keeping the field alive, keeping the field relevant, while our computers catch up, our experimental techniques catch up, and maybe one day, generations from now, we have a hope of beginning to understand these processes. But what do we understand thus far in what, maybe 5 minutes, if that, before I close out the lecture? We don't understand cognition, we don't understand thought, we don't understand learning, and we certainly don't understand consciousness. But we have a general idea of how these things could be possible in the context of the human nervous system. And it's all through the connections of neurons, not the neurons themselves. We understand exactly how neurons fire. Neurons are binary. They fire or they don't. There's an action potential or they're not. 0 and 1. They're functioning like computer chips. It's the networking of neurons that allow these complex patterns to emerge. This is a real diagram of a neuron. So what are you looking at? You're looking at a portion of the dendrites and the soma, the cell body of the neuron. On the left, that's what you see in what, gold, orange? And on the right, that's what you see in green. All of the white squiggles that you see overlaid on top of the dendrites and the soma, and then the real experimental diagram is everything that you see in red on the right, is a synapse. Each of those little squiggles is an axon terminal, and that axon terminal is creating a synapse with this postsynaptic cell. So we see the soma, the cell body, and the dendrites of one postsynaptic cell, and we see the axon terminals of, do you want to count them? Because I certainly don't. We see the axon terminals of dozens and dozens of cells. So this one postsynaptic neuron has the capacity to receive excitatory and inhibitory information from nearly 100 presynaptic neurons. And that's allowing this fine tuning of a binary system. Just like computers, even though each neuron is yes or no, fire or not, one or zero, the complexity of the encoded information is due to how many ones and zeros there are being received by the postsynaptic cell. That's the richness, the depth of the information. So this neuron might be firing and releasing neurotransmitters, and this one's not, and this one's firing, and this one's not, and this one's firing, and this one's not, firing and not firing. And then within that, when this one is firing, it might be releasing GABA. When this one is firing, it might be releasing glutamate. It might be releasing an excitatory neurotransmitter. It might be releasing an inhibitory neurotransmitter. So all of these different signals coming from all of these presynaptic neurons are integrating and coalescing on this postsynaptic neuron. And this postsynaptic neuron will fire or not fire due to the sum total of that information. And when this neuron fires, its axon terminal becomes one of these squiggles on the next neuron that's receiving information from hundreds of other cells. And so the networking of the nervous system is insanely complex. And because the networking, the connections, the number of connections is so complex, the computational power of the brain is remarkably complex. And so what makes the brain so capable is not the architecture of the individual neurons, but the patterns of the connections between them and the signals that are conveyed through the firing and not firing of presynaptic neurons. And the added layer of complexity that some of those are inhibitory and others are excitatory. As these many dozens or hundreds of presynaptic neurons pour their neurotransmitters on this postsynaptic cell, these signals, this information is integrated and combined, allowing or not allowing this postsynaptic neuron to fire, and that information is then part of the complexity of the next postsynaptic neuron. It hurts me to even contemplate, but the brain is nothing more than a finely connected, complex network of organic material that through those synapses can encode information, process information, and store information. Thought, memory, comprehension, emotion, contemplation, executive function, planning is all happening not in the neurons, but at the synapses. So, what did we talk about today? Well, we started talking about selectivity filters. Selectivity filters is what allows individual ion channels to allow only a specific ion or type of ion to pass through, and they're based on the size of the ion and its charge. Then we moved on to gated ion channels that can open or close in response to specific stimuli, mechanical stimuli, voltage-gated stimuli, ligand stimuli, and it's through these gated channels that cells can regulate ion flow and membrane potentials. Membrane potential itself is a measure in voltage, millivolts, of wanted flow of specific ions. And they are possible because ions are unevenly distributed across the membrane, creating an electrical chemical gradient. The resting membrane potential of most cells is somewhere between -20 and -200 millivolts, and it's maintained by ion gradients, specifically a sodium gradient where sodium is outside the cell and a potassium gradient where potassium is inside the cell. And when the membrane potential is at rest, potassium's kind of meh about its flow because it's negative inside the cell, makes potassium happy. It's positive outside the cell, which repels potassium. But it's sodium that really drives the membrane potential. Sodium desperately wants to get into the cell. What's an action potential? An action potential is a wave of sodium influx that propagates unidirectionally down an axon as sodium rushes in, depolarizes that local part of the axonal membrane, and causes the next set of sodium channels to open. Sodium rushes in, depolarizes that patch of the axonal membrane, causing the next patch of sodium channels to open, and so on and so on. So it's all driven by voltage-gated sodium channels. Sodium channels open first. That's what is the actual action potential. This rapidly depolarizes the membrane potential, making it positive. That's going to trigger the opening of potassium gate of voltage gated potassium channels. Potassium goes rushing out of the axon, initially restoring the axon to its resting membrane potential. Then we need the sodium potassium pump to put all the ions back to where they should be. Communication of neurons occurs at synapses, these gaps between neurons, only about 20 nanometers wide, but it is a gap where the electrical signal within the neuron is transformed into a chemical signal. And the essence, the manifestation of that chemical signal is in neurotransmitters. Neurotransmitters are the chemical molecules that relay signals from one neuron to the next. Some neurotransmitters can be excitatory. They slightly depolarize the postsynaptic neuron, getting us closer to the threshold potential that's going to have sodium channels open in that postsynaptic neuron. That makes it more likely that an action potential will be fired. And some neurotransmitters are inhibitory. They hyperpolarize the membrane, a fancy way of saying they make the membrane potential more negative, moving us further away from the threshold potential, making it harder for sodium channels to open in that postsynaptic neuron, thereby making it harder for an action potential to fire. And then we talked a little bit about psychoactive drugs, Valium, Ambien, and we talked about SSRIs as well, and how by mimicking neurotransmitters and controlling those synaptic channels, we can influence perception and how the brain is experiencing life for all intents and purposes. So yeah, so that's it. Oops. Hopefully you enjoyed that and got something out of that. That's going to close out chapter 12 for us, and we will move on to whatever our next topic is next week. I don't even remember. But yeah, you know what to do. Let me know what you'd like to review in class about this material, and I'd be happy to do so. As always, thanks so much for watching.